saw various facets of addition. I mean, it's kind of laughable that we are concentrating so much on addition, but fortunately or unfortunately, all the big things they are based on addition only. So addition is very big thing. Okay, like we can add things like one by one, or we can, if addition is smooth in the sense that it is continuous, like 5 into 5, 10 times, 12 times. Then we go for multiplication, or we have seen other ways to add for addition. But the common thing among every type of addition is calculating the rectangle. And we saw that if we go by rectangle, then slowly we move to kind of mathematics where we have kind of a line function algorithms and these kind of scenarios. So we have independent variable and we have dependent variable. Generally, independent variable we draw on x-axis and a y-axis as dependent variable. And if we describe that like if x is an independent variable and fx is independent, then based upon the fx, we draw the kind of graph and we calculate the area and we get the addition. If we want a part in the area, okay, like how much is the area between this and this, then we can calculate full area of the second part and first part and we can do subtraction, and then so that is called integration, kind of lower limit and upper limit. So that we saw. So we kind of it's pretty nice. Like we have a theory, we have all the science, but it needs corroboration. It needs to be proved. If I am saying that calculating area, calculate for one like sine wave we achieved, but little more if complex if we do, then probably kind of it will be more useful. So we'll see lab session, like suppose that I have a kind of sphere like Earth. Okay, so I have Earth map, Earth globe with us, and I'm searching for a place. Like I'm searching for a place called Al-Qaeda, and it is in Egypt. So wherever the globe is, from there it would rotate and it would stop at a kind of longitude that meets the Al-Qaeda. Then it will rotate. And then it will kind of twist in through latitude and it will show the Al-Qaeda at the center. So this is the requirement. Okay, so it's not very difficult. Means we can rotate and where the longitude of Al-Qaeda, there we can stop and then we can kind of tilt again for the latitude. Okay, but what is kind of limitation is that whatever we are searching, like globe is at one position, whatever we are searching, okay, that should reach in constant, like I'm saying in 5 seconds. Okay, like I am making some video and prior to the video I am showing where it is. So depending if it is very far, it should not take 20 seconds. If it is near, then in 1 second. So it should take constant time, like 5 seconds. If I am showing a place in kind of Siberia, or in one place in Alaska, or one place in Antarctica or Australia, okay, everywhere it would take same time. If it takes same time, then rotation speed will be different. one thing. Second thing requirement is that Earth should not rotate at a speed and suddenly it should stop. It should start with a high speed and gradually it would lessen the speed, and where it meets the longitude, then it will be almost zero. So that someone should see slowly that it's like a train, that it cannot stop at a station immediately. Means from some distance it will start kind of reducing the speed, and then it will stop. So that way it will start at very high speed and it would reach the longitude at almost, it would stop right there and it will keep decreasing the speed. Okay, so I know how much time it would take to reach there. Okay, I know I know the longitude where the at the beginning the globe is and where it has to come. What is the initial speed? Now, when I talk about x and fx, then I'm considering fx as minus x. Okay. So, initial speed is kind of minus x means if it is 10, okay, rotation is in whatever a unit it is, 10 unit per second, then next second it would be 9 and 8, or it has to finish in 5 seconds, then 10, 8, and near 5 seconds it would be almost 0. Okay, so it is kind of reduced in a linear manner. We can go for kind of sinusoidal or x square or what, but right now requirement is minus x kind of thing. It will reduce like a ramp. So if I know that it should reduce like a ramp, and I know total time, I know what is the initial longitude and final longitude, can I find the initial speed at which globe will start rotating, and then second by second it will start rotating slowly, and at the end when it reaches, then it will be almost. Okay, it is similar like a person is walking, okay, and like he is in market and he is walking to home, and he has only 10 minutes. But problem is the way human walk. Initially they can walk very fast, but gradually they decrease the speed. So if he knows that he has to kind of walk maybe 2 kilometers, and 2 kilometers he has to reach in 10 minutes, something like that. Then at what speed he should start his walk, so that if he gradually reduces his walking speed, then by the time he reaches the home, he will be kind of at the rest. Okay, so that is the question. So how we can find this through? So we want to know the initial speed. Okay, because final speed we know 0. Time duration we know that in 10 minutes he has to reach. Distance we know. What would be his initial speed? So that will calculate through integration, and then we'll know that how useful it means. We cannot do by any other means. Okay, simple addition and subtraction would not work. Means power injection is required to come to this. But this is the simplest in integration. Okay, if fx is not minus x or similar to that, then it can be much complex to any degree, and later it may reach to differential equations and those kind. But still, if we have started integration, then this one will see. Okay, so as per discussion, we will move to lab session. So prior to lab session, I believe I can share more things. Okay, so whatever we have covered, so I would summarize because it will kind of little complex now. So what we have done is we now we have some kind of understanding in integration. If it is constant, then it is rectangle, and if it is a ramp, then it is a triangle, and so and so. So what we have seen, like if we have a fx and dx, we consider it as fx ds from 0 to t, and now it becomes fix, fix, that is the integrated value, and it ranges from 0 to t. So this is what we have seen. I think we can add more to it. Okay, so here then up post that, so it will be like so post that it would become like okay, integrated value, and x would be replaced by 0. So this is the default nature what we have seen. So ft minus f0. Okay, so finally it would lead to f integrated t minus f integrated 0. Okay, so this is what we have seen. If I have fx dx, it would convert it to fx ds 0 to t, and fix, that is integrated one, and t, then fit minus fi 0. So upper limit minus lower limit. So this is what we have seen. Now if I just say integration of the dx, then it becomes like x to the power 0 dx, and it is x. And if I say integration of x1 means x dx, it becomes x square. So this is triangle. This is triangle, area of triangle, and this is rectangle. Okay, so rectangle in the sense that x into constant. Now constant is 1, so only x, and here x square by 2. So now with this we come to a conclusion like if it is x power k dx, then it is x to power k plus 1 by k plus 1. So as I stated, the integration starts with kind of smaller things, and then slowly it leads to kind of complex items. Now we'll move for kind of sin x and cos x. So sin x, the series, sin x series is x minus x cube plus x5. This is the sin x series, and this is cos x series. Now if I do sine of t1 to t2 sin x dx, then now we'll do one by one. So x would change to x square by 2, x3 would change x to the power 4 by 4, and 4 into 3 this combination, then it would become like 3 factorial, so it would become like 4, and then x to the power 6 and 6 factorial, and x to the power 8 and 8 factorial. So it would become like this: x square by 2 minus x to the power 4 plus x to the power 6 and t1 minus up to t1 to t2. So since integration is an area, so it has a range. Area cannot be in single dimension, so it has a range. Now for cos x, if I see 1 minus x square, so this is what it is. So whatever we have achieved here, so that is from here to here. This is what we have achieved. So full, if I take okay, so on left side of equal to and cos x I bring right side, then it becomes 1 minus cos x. So integration of sin x dx is 1 minus cos x. Now t1 to t2, so that leads to 1 minus cos t2 minus 1 cos t1. So minus 1 and plus 1, so becomes 0. And this is minus cos t2 minus cos t1. This leads to minus cos x. If it is minus cos x, then t1 to t2, if I say, then it would be minus cos t2 minus cos t1. Okay. So finally, the integration of sin x is minus cos x. Now what is integration of cos x? So 1 would become x square would become x to the power 3 and factorial 3, x to the power 4 would be x to the power 5 factorial 5, so it is same. So integration of cos x is sin x. So we can see we started with a constant, started with a rectangle, and we came to a formula, started with a triangle and we came to a formula, then which led to a kind of a common formula. With that we calculated for sin x and cos x. So this is the integration. So this way we can find for exponential, logarithmic and so many things. So if anything depended upon sin x and cos x, so we know what is the formula. So from the base stuff, so that's why it is said that in mathematics the most basic thing is addition. So from addition, multiplication, integration, then integration of constant item, then variable item, slowly we came to sin x and cos x, and then we'll move for too complex. Okay, anyways, so now we have seen that if I have a triangle and which has equation as, now we came to a kind of independent variable and dependent variable. So if dependent variable is phi 2 by h, then how we find the area? Now in lab session, as per the discussion, okay, so a man is walking and he knows that he is in a kind of market and he is coming to home, and he would start at y km/h speed and he would decelerate at a kind of a constant rate, and when he reaches his home, that is after d minutes or seconds or hours, whatever, his speed is 0. Means he came to normal, means he just reached his home. Okay, he started with a high speed and slowly he reduced his speed at a constant rate, and when he reached his home, then his speed is 0 and he took d unit. Okay, if that is the case, then at what speed he started if he has to cover a distance? Okay, now this person knows that he has to travel a distance kind of 5 kilometers, and 5 kilometers he has to reach in 2 hours. Then 2 hours means d equal to 2. 5 kilometers he has to travel. Then y is the initial speed. At what speed he has to start, so that when he walks for 10 kilometers, after d hours, he'll come to rest and he enters the home. So, okay, so if that is the scenario, can we see this is the equation of a line? And if this is speed, then if I integrate it, then area becomes kind of total distance. Okay, so this line is equation of a line. Okay, so this line is equation of a line So this line is equation of a line. So this is a line now. It should be pretty clear. Now this is a line. This is a line, and this is the kind of it talks about speed. Speed in the sense that at any moment how much distance he is collecting. The way we discussed earlier, at any moment how much is the distance that he collected. So that leads to speed, and if I see speed at 0 is y and speed at d is 0, and this is a line, can we come to a kind of equation like this? 0 minus y by d, t is any time plus y. So this is the equation of the line. So, okay, if time is 0, okay, this whole stuff becomes 0, and here the speed is y. If time is d, then d by d is 1. This leads to minus y plus y equal to 0. So at time d, here the speed is 0, and at time 0, speed is y. Now I have to find the area. If I find the area, I would say the distance covered, how much distance he covered in d time. So area of this from 0 to d. Now the way what we have seen, okay, so now we can denote it as ty dt. I would rather say it should be in braces. Okay, so it is in braces, the way we say. Okay, so complete equation dt means we change it to dt, means this is what the fashion is. Whatever is the variable, so t is variable, so we call it dt. Now, if I see the integration, then integration of the t is t square by 2. So this become like this, and yt d to 0. So this will become minus d square by and this much. Okay, so now if I take out y and then we do shuffling, then initial speed would be distance covered into 2 by d. Okay, so this 2, I believe this is what is correct. So y if I take out, okay, I hope this is correct. Okay. So why the initial speed is total distance covered by d if it is reaching in d. Okay. Now what about now we talked about d. What about its speed? Okay. So we talked about at what speed he would start. If I know he started at speed y, then how much distance he has covered at any moment t. So this is the distance total covered at t. So at any moment t, so this is the distance covered. Okay. So this is what anyway we have seen, but it is crucial because this is our lab session. So in lab session, what we'll see is we'll place longitude and latitude of a point in Earth, and Earth should start at a speed that is y, and it has to rotate till it reaches the latitude and longitude what we have specified, and when it is reaching at that point, the speed should tend to kind of zero. It would very slowly it would reach this point. Okay. Then this is secondary thing, that it would rotate again for latitude and then it would show it. Okay. That also we can manipulate speed wise. So initially the latitude movement also will be at high speed if it is up, and then it will slowly come here. So how much distance we are traveling? Can we see? This is not linear distance. This is angular distance. So suppose that Earth is at 0 beginning and longitude is 170, then it has to rotate 170 degree angle. Okay. So distance covered, we are talking about distance covered. So we know distance covered, like here, we know distance covered. Distance covered is 170 degree, or we can make in radian, into 2 by how much time it takes. So idea is it should take constant time. Okay, like if it is reaching this point, okay, or so if it is moving 170 degree, or it is moving 720 degree, or it is moving 340 degree, okay, it would take same time. If it is taking same time, distance is different, and then certainly it has to start with a different speed and then slowly it would reduce. So that we'll see in lab session, that how actually it look. But this is the concept that we'll follow. So first is we'll know what is the initial speed, and because we know total angle it has to cover, and into 2, and how much time it has to face. If total distance to cover is very high, otherwise these are constants, so in beginning speed will be high. Okay. Now every moment the globe is rotating. Now I know y. Okay. I know t because I know how much time has been spent, or time span, how much time span is over. Okay. And what is the total time, that at any moment we can calculate how much distance it has traveled. If I know how much distance it should travel by this time, and how much distance it has traveled by now, then it would help us in rotating the globe. That's why there are two diagrams. First is to find the initial speed, and second is to find the distance covered at any moment. If these two we know, then we can begin with the initial speed rotating the globe, and after that any moment we can see how much it has rotated and how much it has to rotate by now, so we can quickly rotate that to that extent. Okay, so that we'll see in the lab session.